All right, so now let me talk about partial pivoting. Okay, and so the basic idea behind partial pivoting is that this is a procedure, it's like which one does during the LU decomposition process, where we allow you the possibility of reordering the equations so that the entry, it's like with the largest pivot, is used as the sort of the equation. It's like which you add to the others to zero them out. Okay, so let's see what happens. So you have some process of identifying what is the best pivot to pick in that column. So you pick along this column. So you might search for the entry of the largest absolute value, for example. All right. And then you want to apply a permutation, that's called a P2. And what the effect of the permutation is to do is to exchange these two. You want to exchange these two rows. Okay. Then xik now is that entry. And then, of course, as before, it's like you want to do the elimination step, right? Which is obtained using this B2 operation. And B2 zeroes out the entries below the diagonal by adding an appropriate multiple of that equation. Yeah? And the crosses there don't really mean the same value, they just mean that it's some value which we don't know. Okay, so the first step involves selecting a pivot. Okay, once you've selected the pivot, you do this row exchange. Exchange the rows. Then once you've exchanged the rows, you can use that equation to eliminate the other two terms. Okay, so that's just some sort of heuristic picture of what's going on. So what happens is that with no pivoting, right, what you have is some sort of bn minus 1, bn minus 2 up to b1 acting on a is equal to u. All right, and if you do partial pivoting, and what you're doing is bn minus 1, p n minus 1 all the way up to b1 p1 a is equal to u. All right, so so let's look at an example, okay, of what is involved here. Okay, so all right, so let me try to get the original problem. All right, so let's say A is the following: 2 1 1 0 4 3 3 1 8 7 9 5 and 6 7 9 8. Okay. All right, so I first try to identify the pivot, right? So I look at this column and I see that 8 is the one which is the largest. So what I want to do is I want to interchange rows 1 and rows 3. Okay, so I start with the identity matrix 1 1 1 1, and I interchange rows 1 and row 3. This gives me 0 0 1 0 0 1 0 0 1 0 0 0 0 0 0 1. This is what I call P1. Okay. All right. So okay. So P1 acting on the matrix A has the effect of interchanging rows 1 and rows 3. So P1A is equal to 8795 4331 2110 6798. Okay. All right. So now I can, use elementary row operations to take multiples of this first row and add it to any of these other three rows. Okay. So let's go ahead and do that. So this is B1, P1A. All right. Okay. So B1 has a diagonal of 1s, right? And the coefficients involve each of these entries divided by 8 with a minus sign, right? So the first entry is 4 divided by 8 with a minus sign, that's minus 1/2. Okay, the entry here is 2 divided by 8 with a minus sign, that's minus 1/4. Then it's 6 divided by 8 with a minus sign, that's minus 3/4. So that's B1 times PA. All right, so that's 8795 4331 2110 6798. Right, this is B1, this is P1A. Okay, so that's equal to 8795,000 minus 1/2 minus 3/2 minus 3/2 minus 3/4 minus 5/4 minus 5/4, then 7/4, 9/4, and 17/4. All right. So now, again, this first column below the diagonal has been zeroed out. I now want to look at these entries to look for a pivot. So that's something which has largest absolute value. You'll see that the thing with largest absolute value is this entry. So now I want to interchange rows 2 and rows 4. Okay. So that's P2, B1, P1A, interchanging rows 2 and 4, right? So again, you can check that if you take the identity and then you interchange rows in 2s and 4, you get the following matrix, which is a permutation matrix. So it's easy to check something as a permutation matrix. There's exactly one and only one entry, which is 1 in each row and column, right? So if here, right, there's no more 1s along that row, there's no more 1s along that column. Again, no more 1s along that column or that row, and you can sort of check that, right? Okay, so this is B1, P1A. Okay, and again, all this does is to interchange rows 2 and 4 of this matrix. Okay, so that's 8795, 0, 7/4, 9/4, 17/4. Okay, 0 minus 3/4 minus 5/4 minus 5/4, and 0 minus 1/2 minus 3/2 minus 3/2. Okay, so now I'm using this to zero out these two entries. Okay, so that is B2, P2, P1, B1, P1A. That is, all right, so 8795, 0, 7/4, 9/4, 17/4, 0, 0, 0, 0. They're just these two entries here. Oh, I'm sorry. I should write down what B2 is, so 1, 1, 1, 1. Okay, so these are the two non-zero entries. Minus 3/4 divided by 7 over 4 with a minus sign, that is 3 over 7. Then minus 1/2 divided by 7 over 4, again with a minus sign, that's 2 over 7. Okay. All right, so that's then P2, B1, P1A, that's going to be equal to 8795, 0, 7 over 4, 9 over 4, 17 over 4, 0, sorry, so 0, minus 6 over 7, minus 2 over 7, 0, 0, all right, there's some entries which I don't quite know yet. Okay, anyhow, all right, so finally, after everything's said and done, I mean, you do one more step, all right, and then what will eventually happen is that you get B3, P3, B2, P2, B1, P1 acting on A is an upper triangular matrix, which is of the form 8795, 0, 7 over 4, 9 over 4, 17 over 4, 0, 0, minus 6 over 7, minus 2 over 7, 0, 0, 0, 2/3. Okay? All right. Okay. So, right. So now, if you recall, it's like at least without the permutation matrices, right, these things which pre-multiply A, the inverse of that becomes a lower triangular matrix. So this gives you, you know, it's like this this expression which you want. So let's see how, you know, how we can manipulate this when there are permutation matrices in it as well. So there are some observations to make. Okay. Okay, so there's a bit of luck which comes into play, so more luck in this construction. So if you let B3 prime be B3 and B2 prime be P3, B2, P3 inverse, and B1 prime be P3, P2, B1, P2 inverse, P3 inverse, and so on. Then the claim is as follows, that B3, P3, B2, P2, B1, P1 looks like the following. Okay, so this becomes B3 prime, B2 prime, B1 prime, P3, P2, P1. And the proof is straightforward. It really sort of just involves substituting, it's like these identifications, it's like into this expression, and then using the fact that, you know, it's like these inverses, it's like of the permutation matrices will cancel out, it's like the permutation matrix itself. So let's just see what happens. Not really a proof, but maybe a calculation. So B3 prime, B2 prime, B1 prime is equal to B3, P3, B2, P3 inverse, P3, P2, B1, P2 inverse, P3 inverse. Okay, so this cancels out, it's just the identity. Okay, so this is just B3, P3, B2, P2, B1, P2 inverse, P3 inverse. Right? So we wanted to show that this product times this is this expression. So we've evaluated B3 prime, B2 prime, B1 prime. So B3 prime, B2 prime, B1 prime multiplied by P3, P2, P1 looks like B3, P3, B2, P2, B1, P2 inverse, P3 inverse, P3, P2, P1. So this cancels out to give you the identity, and then P2 inverse times P2 again gives you the identity. So now you're left with B3, P3, B2, P2, B1, P1, which is the left-hand side which we were trying to get. All right, so what's the net effect of this? So this basically tells you that by appropriately transforming these matrices, which correspond to the elementary row operations by the permutation action, okay, you can rewrite the expression which you had, which was originally that B3, P3, B2, P2, B1, P1 times the A matrix is equal to U. I can rewrite this now in terms of this and this. So this is B3 prime, B2 prime, B1 prime acting on P3, P2, P1 times A is equal to U. All right, and then as will happen before, these expressions have some nice ways of writing it down. Okay, so some observations and remarks. So the inverse of a permutation matrix is just its transpose, right? So the transpose just involves mapping rows to columns. Okay, so that's the first observation, that the inverse of a permutation matrix is just its transpose. The second of which is that P, which is this product of permutation matrices, P3, P2, P1, is again a permutation matrix. And then the third thing is that if you look at the inverse of this thing, L, which is defined to be B3 prime, B2 prime, B1 prime inverse, this is again lower triangular with ones along the diagonals. All right, so what this is sort of more or less saying is that instead of having A is equal to LU, you have something which looks more like P times A is equal to L times U, right? So another way to sort of think about this is that if you take this matrix A and you permuted the entries ahead of time, then you could do LU decomposition on it in such a way that the pivot which shows up on the diagonal is always going to be the one which is maximum in that column. Okay, so yeah, so if you sort of magically knew ahead of time what the right permutation is, then in some sense you didn't need to do partial pivot. Okay, and of course in reality that's not always so easy to do, but anyway, so that's just sort of an observation. And in the context of the matrix which we were working on before, let me just write down what all those entries end up looking like. Okay, So PA is equal to LU. Okay, so the permutation matrix looks like 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0 times A, which is 2, 1, 1, 0, 4, 3, 3, 1, 8, 7, 9, 5, 6, 7, 9, 8. So this is PA, this is A, and L is this lower triangular matrix, 3/4, 1/2, 1/4, minus 2 over 7, minus 3 over 7, and 1/3. And then U is 8, 7, 9, 5, 7 over 4, 9 over 4, 17 over 4, minus 6 over 7, minus 2 over 7, and 2/3. Okay, so this is what it looks like. This is the lower triangular matrix, and this is the upper triangular matrix. All right, so that's just an example. And then it's like what we'll do next is to show you how to actually compute all these entries sort of systematically, and then I'll present a pseudocode for the actual algorithm as well. Okay, so let me just stop here for now.